Section 2.1 about limits. Okay, so limits, guys, it's a tool we use in calculus. It's conceptual. It's an idea. And the scariest part of limits, y'all, is the notation. A lot of calculus, the scariest part is notation. It's like seeing this new way of writing stuff for the first time, but it's all ideas from algebra. It's all ideas from algebra. So just remember, this is very like a conceptual idea that we're about to talk about. So what is a limit? What is a limit? Oh, sorry. I hear something in the chat. Let me pop over there. Cassandra, go ahead. Oh, yes, Cassandra, I am recording this. So this is being recorded.
Okay, thank you.
Yeah, no worries. Okay, so what is a limit? We're going to start by thinking about a function. And I put a really fun one on here. I put a rational function. So this function is a rational function. It's a rational because it's a fraction. There's a numerator and a denominator. Okay, so what is a function? We're just going to start by looking at the graph of this function. And something interesting is happening on this graph. There's a hole in this graph. So what is happening when there's a hole in the graph? So when x equals 2, down here, when x is 2, the graph of this function, now remember, the graph of a function shows all the solutions to the function, right? So when x equals 2, there's a hole in this graph. Well, what's happening? So what I did here is, here's x equals 2. I plugged in values getting closer and closer and closer to 2 from the left, and getting closer and closer and closer and closer to 2 from the right. That's what I've done here. So when I plugged 1.7 into the function, when I put 1.7 into the function, so 1.7 is like right here somewhere, the height came out to be 3.7. And then when I put 1.9 into the function, so I got even closer to 2, the height was 3.9. My height got closer to 4. And then if I got closer and closer and closer to 2, what does it look like that height should be approaching? What number does it look like I should get here? If I was just following the pattern, you can throw it in the chat. What number do you think we should get? Yeah, 4, right? Looks like we should be getting a 4. Okay, so I'm going to put a little 4 here. That's what it looks like. And then I did the same thing on the other side. So I started pretty far away from 2, and then I got closer and closer. So 2.2 would be over here somewhere. And the height was just a little bit above 4 when that happened. And then 2.1, I got a little closer. And then the height got a little closer, right? The height got a little closer to 4. And if I continue that, if I just get closer and closer and closer, it looks like these heights are getting closer and closer and closer to 4, right? But let's see what's really happening when we put 2 into the function. So I'm just going to follow this rule over here. Here's my input. Where's the input being sent? It's being sent to the numerator and the denominator, so I'm going to plug that in. So when I put 2 into the function, I'm going to end up with 2 squared minus 4 over 2 minus 2. So that's going to give me 4 minus 4 in the numerator, that's 0. And 2 minus 2 in the denominator, that's 0. Uh-oh. Does 0 over 0 equal 4? No. What happens when we have a 0 in the denominator? What do we say when we have 0 in the denominator? Do you remember what that's called? Yeah, undefined. It's undefined. That's right. So this is undefined. This function is undefined when x equals 2. That's why there's a hole here. That's why there's a hole. But this function works everywhere else. Any other input, any other real number, negative, positive, fraction, decimal, any number that I plug in except for x equals 2 is following this really predictable path, right? There's just this one time the function freaks out. So to handle this idea that I could zoom in really, really, really close from the left and really, really close from the right, and there's only this one part that freaks out, to handle this, we introduce something called the limit. So in calculus, we're going to introduce this idea of a limit. And this is what we're going to say here. We're going to say that the limit, so here's our notation, the limit of our function, f of x, as my x gets really, really, really close to 2 from the left and the right. The limit of the function is 4, even though the actual value of the function is undefined. So we're going to formalize this in a minute, but this is the notation. And sometimes instead of the function, the f of x, they'll actually put the rule in there. So sometimes you'll see them put x squared minus 4 over x minus 2. That right there, this is just your f of x. So they can just put generic f of x, or they can put the rule in there. But the idea is that if you zoom in, think about limits as zooming. If you zoom in to x equals 2 from the left and the right, from both directions, what is the height getting really, really close to? So remember, when you have f of x, that's always an output, right? It's the result of putting x into a function. So this is always describing the output. Your limit is always going to describe the output, or which is the height of the function. So that's the height of the function. So limits are always describing heights. Now, of course, we're going to formalize this a little bit. So what we're going to say here to make a limit be true, and this is a theorem I'm going to show you in a minute. This is what we say. For a limit to actually exist, when I look from the left, the heights have to be approaching the same number as when I look from the right. So we have different limit notation for that. When I'm looking from the left, I'm going to say that's the limit as x approaches, in this case 2, right? We're zooming in on the input 2. From the left, that we put a little negative sign there. The negative sign means we're going to look from the left. We're zooming in from the left. So zooming in from the left. So as I zoomed in to this function from the left, the height was getting closer and closer to 4. And then on the other side, as I zoomed in from the right, it's also getting close to 4. So we have notation for that too. We're going to say it's the limit as x zooms into 2 from the right. So we put a little plus sign there to show we're zooming in from the right. So let me write that down. This is zooming in from the right. So the limit of my function, so the limit of f of x as my input x is zooming into 2, plus sign means from the right, that height was also going to 4. So the height on the left was going to 4, the height on the right was going to 4. If these guys match, then we say the limit exists in general. So then we say up here that the limit of the function as my input is zooming into 2. If you see 2 without a plus or minus superscript, that just means 2 in general from the left and the right. So input from left and right. Overall, the limit from the left and the right is going to 4. Okay, so there's a question. So Arjana, you can either type or talk out loud.
Sorry, you said if those match, then what? My mark is gonna cut out for a second.
Oh yeah, no worries. If those are matching, then the overall limit exists. So the limit in general, so from the left and the right. So let me write this down here. This is the overall limit from the left and the right. Because a lot of times, especially in business calculus, when your functions are really yucky, you won't have a graph to help you out. We're going to have to do this more algebraically. So the way we're going to check it algebraically is we're going to look from the left. We're going to plug in things from the left. We're going to look from the right. And if those are matching, then we're going to say overall there's a limit that exists. If they don't match, there's not a limit. And I'm going to show this to you. And another reason why we want to see this is because this hole that is I wrote like really exaggerated on your graph does not show up when you try to graph this on a graphing calculator or in Desmos. So let me show you that real quick. I'm going to graph this on Desmos real quick, or you can, if you have a graphing calculator, go ahead and graph this just to remind ourselves that that hole does not appear. So I'm going to share Desmos. I'll be using Desmos a lot because it's an easy way for me to demonstrate graphing calculators. So let me share Desmos over here. And Desmos is allowed on your test. You'll be in a lockdown browser, but I will allow the Desmos website to pop up. So it's free. It's nice. It's easy to use. Let me see. I'm trying to share that. So let me graph this in Desmos. Okay, so here's Desmos. Desmos has a lot of different calculators. I'm going to the graphing calculator here. And I'm just going to graph this real quick. So my function was x squared minus 4. And I'm putting that in parentheses because all that needs to be in the numerator. Divided by, was it x minus 2 or x plus 2? Let me see. It was x minus 2. Okay. Oops. I need to keep that in the denominator. X minus 2. Okay. And here is our graph. Let me clean this up a little bit. I'm going to take the minor grid lines off and I'm going to count by ones. Okay, so here's our graph. And see how that hole's not showing up there? That hole is not showing up. So if I wanted to do the function exactly when x was it 2? Yeah, when x was 2, see how when I plug 2 into the function, it's telling me undefined, but I don't see, oh, here it is. I don't see a hole there. It doesn't, and your graphing calculator won't show you a hole because it's such an like tiny, tiny, tiny little blip on the radar. It's just this infinitesimally small like blip in time when x is 2. Like it doesn't matter how much I zoom in there. I'm not going to see, I'm zooming. Like you can look down here on the x-axis and see how zoomed in I am to 2. I still don't see that hole. It'll never show up. So your algebra knowledge has to be what reminds you there's a hole there because the function is actually undefined at that point. Oops. Oh. And if I had wanted to get those other values, I could, when the function was 1.999, I'm going to get really, really close to 2. See how close to 2 I am there and how close to 4 the height is, the output is? And then on the other side, I can get really, really, really close to 2 again. 2.00001, super close, and I'm really close to height of 4, but I'm not actually there. And I never actually get there, but that's okay. So there's a question in the chat. So let me pull up there. So the hole in the function is because the domain was all real numbers except for x equals 2. So it's a hole because it isn't included. That is correct. Will all limits be where the function is undefined? You can find a limit at any single point you want, but we only really use them for the interesting ones. So the limits are like an investigative tool. So if, for example, I could find the limit when x is 1, and I'm going to show you how to do that algebraically, and that the limit's just 3, because I can see the height of the graph is approaching 3 from the left, it's approaching 3 from the right. If I actually plug 1 into the function, it gives me a 3. So we'll still follow the definition of a limit at a point like where x equals 1. It's not a tricky point, so we didn't really need to go to all the effort of a limit. We really only use these limits to figure out like tricky situations. Good question. Okay, so let's go back to the notes. And James, I think as we explore some more of these limits, we'll do some that aren't tricky and some that are. Maybe it'll help kind of like solidify that idea a little bit. Okay, cool. So let me navigate away from Desmos here. God, what did we do before Desmos? Desmos is amazing. And then I'm going to go back to our notes. And let's talk about what this definition looks like. When you click the help tools on MyMathLab, what in the world is it going to show you here? It's going to show you this. Here is your formal definition. Okay, let's read through this. I promise the notation is the scariest part of limits. So let's read what this definition is. If you need help on MyMathLab, it's going to pop up this definition. And I don't want you to be intimidated. You can read through this, okay? It says one-sided limits. That's from either the left or the right, not overall, okay? One-sided. It's saying let f be a function. So f is some kind of function out there. And L and C are real numbers. Those are just some kind of constant number out there. Decimal, fraction, negative, positive. I don't know. It's just some kind of real number. So the first bullet point says the limit of the function from the left of C, so C is going to be some kind of input, is L. So C is just a number, L is just a number. So let me actually write down some little notes here so you don't freak out when you see this definition later. Oops. Sorry, something popped up on my phone. There it goes. Okay. Okay, so what in the world is this up? So C is going to be your input. This is going to be your input. And L is going to be your output. So as you're approaching C, that's some kind of input. As you're approaching that input, you're going to approach some kind of output. So this is what that notation looks like. You know, here's your input. Right here, this is your input. It's the input from the left. That's why you have that little negative sign. And you're approaching some kind of output. That's the height of the graph. Okay, so from the left has that little negative sign. From the right, if you're approaching it from the right, you have your input with a positive sign. So if you see that plus sign, that's your input from the right. And again, it's just approaching some kind of output, some number there. And that's just your height of the graph. So if that input from the left approaches a number and the input from the right approaches a number, and if they're the same number, so if the limit from the left exists, check, and the limit from the right exists, check, and they're equaling the same number, the same height of the graph, the same output. If that's happening, there's an overall limit. This is your overall limit from the left and the right, from all directions. So that's your formal definition, your first formal calculus definition, y'all. So let's just put this into action so we don't freak out too much. I promise it's not as scary as it looks at first. Everything's scary the first time you see it. And then your brain will get, just embrace the horror and your brain will get used to it. So let's see this in action. Okay, so I'm going to move over here to a problem with a graph here. Okay. So here's a graph, and I just totally made this up. It is a piecewise function to the max. I combined like a gazillion different functions for this. So I didn't define the function. I didn't say function equals and then give you the rule, because I just made this graph up so I could use it over and over again. Okay, so you're just going to see a generic function notation in here. You're not going to see a specific rule. So you can't cheat on this one. You can't plug in inputs and see what the outputs are doing. Definition of a limit. Okay, so let's see what this definition says. Okay, so what is A asking us for? We're zooming in here. It's asking us to zoom in on x equals -1. And it's asking to zoom in from the left. And this is a little bit blurry. Sorry, I should have, I did some snipping tools and pasting, and I should have blown it up a little bit. So hopefully y'all can read that. But it's a -1 with a superscript of -1. So this is going to be from the left. From the left. So what is happening? What is the output doing as I approach x equals -1 from the left? And again, this little negative sign is what's telling me to go from the left. Okay, so let's find -1. It's right here. And I'm going to look from the left. So as I approach this from the left, then what's happening here? My heights are going up, 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 up. And what are they getting closer and closer and closer to? They're getting closer and closer to 5. Okay, so I would put a 5 there. My output is going to 5, a height of 5. Okay, so now let's look at that from the other direction. Let's look at that from the right. Okay, that's what B is saying. See how there's a -1, but now you have that little plus symbol? That's telling us to look at it from the right. So I'm going to approach this number from the right. So as I approach my inputs from the right, you know, as I look at inputs and then see their heights, and I look at an input a little bit closer and I see its height, then I look at an input a little bit closer and I see its height. See how it's also approaching a height of 5? So my output is also approaching a height of 5. Okay, so my output on the left was approaching a height of 5. My output on the right was approaching the height of 5. Do those match? Yep, they match, right? So these guys match. Since they match, I can say that the overall limit, no plus or minus, this is overall. Overall limit. So the overall limit is just going to be a 5. And then it just so happens when I actually look at the graph here, so when I actually look at x equals -1, if I actually focus in on that, see how there's not a hole? There's no hole in the graph. There's no hole. If there's no hole, the graph is actually defined there. The height of the graph is actually a 5. So all of these happen to match, but that won't always happen. We're going to see an example in a minute where that doesn't happen. Okay, so, oh, I hear a chime. Trinity, go ahead.
So, for C, that represents the overall limit.
Yeah, from the left and the right. So the only way you get an overall limit is if the output from the left and the output from the right match. If that's happening, then overall there's a limit to the function at that specific endpoint. So if they match, so if this output and that output match, then you have an overall limit. And that's where, yeah, you don't have any pluses or minuses. So we're going to see some examples where the limit from the left exists and the limit from the right exists, but they don't match. So there's not an overall limit because they're doing different things from different sides. So we'll see an example of that. Okay, and I know all of this is weird at first. Sometimes you have to see lots of different examples before it starts to click. At first you're like, what are we even doing with these limits? I don't know. What's happening? Let's try another one. So let's zoom in on 2 now, because something weird's happening too. We're just going to add some layers on here. Let's zoom in. Actually, just to prove a point, I'm going to jump over here and zoom in on 5 for a second, just because it might help your question, Trinity. So let's zoom in on 5. So I think that's actually number, would that be 1, 2, I think that'd be number 6. So if you printed out the notes, it'll be number 6. If you didn't print out the notes, that's okay, because you're just watching the screen. So I'm going to come over here. We're going to zoom in on 5. Okay. Just maybe it'll help answer some questions, because I know this is really new. Okay, so let's zoom in on 5 now. So this one. We are going to zoom in. We are going to zoom in on x equals 5 now. We're going to zoom in from the left, from the right, overall, and then look at the actual value. So here's x equals 5 on my graph. Okay, x equals 5. And let's see what's happening. The first thing we want to do is zoom in from the left. And I know I'm zooming in from the left because I see a little negative sign there. So let's zoom in from the left. So from the left. What is happening to the output as I zoom in from the left? So I'm zooming in from the left. And what's happening? My outputs, so if I'm at 4, I'm way up here. Then I get a little closer to 5 and my output drops. And then I get a little closer to 5 and my output drops. And I get a little bit closer to 5 and my output drops some more. But does it drop forever? No, right? What height is it getting closer and closer and closer to? And we're ignoring this hole because we're not actually getting to 5, right? But what height am I getting closer and closer and closer and closer and closer and closer and closer to? We're getting closer and closer and closer and closer to a height of 3. I'm zooming in on a height of 3 there. So the output's going to a height of 3 from the left. It started way up here at 5, and then my output dropped a little, and then my output dropped some more, and then my output dropped some more, and eventually I'm getting a height of 3 there. Okay, then we're going to switch it up. We're going to go, part B asks us to go from the right. And the reason why I know it's from the right is because I see that little plus sign there. So that's how I know we're going to go from the right. Okay, so I'm approaching from the right this time. Okay, so let's start over here at 6. So at 6, I have a height of 2. And I get a little closer to 5 and the height is still 2. And I get a little closer to 5 and the height is still 2. And I get even closer and the height is still 2. So what height am I approaching as my inputs get closer and closer and closer to 5 from the right? Yeah, that output's approaching a height of 2. Did those heights match from the left and the right? No, right? These do not match. These guys do not match. If they don't match, if the outputs don't match, then we say that this limit does not exist. There's not a single height that we're approaching overall as we get closer and closer to 5. It's doing different things on different sides. There's not this overall output we're approaching. But was the function defined when x equals 5? I don't know. Let's look. When x was actually equal to 5, if I actually look at x equals 5 on the graph, let's see. So when x is actually 5, there's a solid dot right here. So it's actually defined. The function is defined. An output is defined for this function when the input is 5. And that output is a height of 2. So you're just learning how to read all this different notation. Oh, does it? Oh, man. Okay, are those the notes, Jocelyn, that you printed out from class? I tried to reformat them very quickly before class. Oh no. Okay. Normally I will do a better job of making sure what I'm showing you in class is exactly matching the numbering that you print out in class. I have to change the formatting to make it fit on this little tiny screen I have to write on, but I didn't want y'all to waste a ton of paper. I'm so sorry. So on the notes you printed out, there wasn't anything that had x approaching a 5? Bummer. Okay, I'm sorry. You know what? Maybe I should it's number 6. Oh, okay. Sorry. You know what? I think I'll just have y'all print just to be safe, unless I have time to triple check. Oops. I might just have y'all print exactly what I'm writing on in class. I was trying to be environmentally friendly and not have y'all print 10 pages if you didn't have to. But apparently I'm not cool enough to get my numbering right. Oh no. Hopefully that didn't just totally confuse y'all that had this printed. I'm sorry. Maybe I shouldn't have skipped the order either. I just wanted to answer Trinity's question. Limits are hard enough without me making it more confusing. Okay. But if you were following along on this problem and you weren't too freaked out with the numbering, throw me either an emoji or a status or something so I can see how you felt about this explanation, about this idea of the heights not matching from the left and the right, so the limit doesn't exist. How are y'all feeling? So you can change your status at the bottom of your screen by clicking your... okay, some people said they understood it in the chat. Oh, sad face. I know. If you're not understanding it right now, that's okay. We have some more examples. Got some happy faces out there. Okay. So if you're feeling like vomiting right now, that's okay. So we'll see some more examples. There's a question in the chat right now that is asking, Omar's asking, does the function have two outputs? No, it does not. So when I look here at my function, when x equals 5, there's a hole. So if there's a hole, that means it's undefined right there. There's not, output is missing. Output is missing at that hole. So, but there's a solid dot here. This is a solid dot. So that's where the function is actually defined. Good question. Okay, cool. Okay, y'all. Ooh, strong. I like it. Okay, so let's go back to the problems I skipped that messed us all up here. Okay, so where were we? Okay, so let's go to number 3 on my notes. I have no idea what it is on what you printed, but what we're going to be focusing on for this one is the number 3. The number 2, x equals 2. So find the problem on your notes somewhere where you're focusing in on x being a 2. I'll give you a second to find it. Okay, so hopefully you found a problem with this graph that's saying x equals 2. Okay. It's 3 on the notes. No! Oh, man. Okay. My eye is twitching. Okay, here we go. Sorry about that. So let's just take a look at it wherever it is located on your paper. And we are being asked in part A to approach 2 with a negative superscript. That means from the left. So I'm going to approach 2 from the left. Okay, when I do that, let's see. So if I start far away from 2, you know, my height's down here. But then as I get closer to 2, my height's going up. I get closer to 2, my height's going even higher. And as I get closer and closer to 2, my height is getting closer and closer to an output of 4. Remember, the heights of your graphs are always your output. So when you see output, you're thinking the height of the graph. What is the height of the graph approaching? So in this case, it's approaching 4. Okay. And now we're going to approach from the other side here. We're going to approach from the right. So I'm going to approach from the right. What is happening to the heights of the graph as I go from the right? Well, if I start far away from 2, my height's way up here. But as I get closer and closer to 2, my heights are dropping. As I get closer and closer, drop some more. It's dropping and dropping and dropping, but it's dropping. It's not dropping forever. It's getting closer and closer again to this height of 4. So again, my output, my height of my graph is getting closer and closer to 4. Did those match? Yeah, they match, right? If they match, then we have an overall limit that exists, and it's the number 4. The height of the graph in general is 4 because the left-hand side outputs are doing the same thing as the right-hand side outputs. These things are matching, so we have an overall limit. And it doesn't matter what's actually happening when x actually equals 2. Right here, x is actually equaling to 2. When x actually equals to 2, and I come up and look at my graph, there's a big old hole there. So is the function defined? Is there a dot anywhere else? I'm scanning up and down where x equals 2. I'm looking above that height for some kind of definition, and there's nothing. So this is the function is undefined, but that has nothing to do with the limit. The limit is this conceptual idea that's just looking at the outputs from the left to the right. We're just zooming in. We don't care what actually happens there. We just want to know what's happening from the left, what's happening from the right. If it's behaving the same way, if it's doing the same thing, there's a limit. If it's not behaving the same way, if it's not doing the same thing on left and right, the heights aren't matching, there's no limit. Okay, throw me an emoji on this one. Or, oh, go ahead.
Why did we say that 2 was undefined?
Because when I look at my graph, when x actually equals 2, and I look at my graph there, so if I take everything else away here for a sec, and I'm looking at 2, so I'm scanning all this area. The function is never defined. See how there's a hole there? And if there had been like a solid dot up here, then it would be defined at a height of 6. Or if this was a solid dot, then it would be defined at a height of 4. But since it's just a hole, and there's no dot anywhere along that vertical space above 2, it's just undefined everywhere. Does that help?
Yes, thank you.
Okay, cool. Okay, now let's see an example where we have a hole, but it is still defined. So let's try another example. So it's the example on your paper where x would be a 3, and I'm guessing it would be I don't even want to guess what the number is. But we are going to zoom in now where x is a 3. So find that somewhere on your paper. Number 5, okay, let me fix that here. It's number 5 on the printed notes. This one was number 6. So I was just off by one number. Darn you. You know, Microsoft Word auto formats everything, so I must have put a space in there. Anyway, okay. So let's zoom in on this one. Okay, here we go. In fact, I'm going to be quiet just for a second and let you try to answer these, A, B, C, D. And if you get it wrong, that's okay. Just think for a second. Don't put anything in the chat. Just what do you think these answers are? Okay, let's see how you did on these, y'all. So as you approach x equals 3 from the left, hopefully you saw that your heights were getting higher and higher and higher. And they were approaching eventually a height of 7. Okay, and then as we approach from the right, as I approach x equals 3 from the right, start far away from 3, and then I get closer and my heights are getting taller and taller and taller and taller, and they're eventually approaching a height of 7 again. Okay, and then those matched. So since they match, there is an overall limit, and the height is 7. But when we look, when x is actually equal to 3, here's 3. When I look, where's the dot? There's a hole up here, so it's not defined up there. Your function's actually defined at this height, which is a 4. It's a height of 4. So hopefully you got that one right. I don't know. Give me everyone do a status check this time so we don't have a lot of stuff in the chat in case someone's asking a question. So go click your profile picture and give me a status so I can see how you felt on that. Okay, got it. Some happy faces, some confused faces. Okay, for those of y'all who are still maybe a little confused on what's going on here, I'll just pause for a minute to see if y'all have a question. You might be so confused you don't even know what to ask. Oh, go ahead.
How do we change our status? Sorry.
Oh, no, good question. So when you, to change your status, give me 1 second here. You go to, oops, here it is. To change your status, you go to the bottom of your screen where the microphone and the camera and the hand raise are, and you click that little profile picture. And when you do, a menu pops up, and then you can click one of those. And it's just a temporary little status symbol. It lasts about 10 seconds, I think. Cool. Awesome. Okay, y'all. I know this is a lot. Just deep breaths. Okay, let me go back and share my notes now, because we got, so far we've been doing this graphically, but we're going to talk about it algebraically because it's not always convenient or to have a graph. Sometimes you're going to have to think about this algebraically. Okay, so you'll have a lot of practice on your homework. Don't worry, my math lab will give you lots of these graphs where you'll be typing these things in, and you'll have some help tools. You can rewatch this video. Okay, we're going to talk about how to do this algebraically now. And I bet all these numbers are thrown off now because I'm guessing this should be number 7 on your notes that you printed. So let me change that. Number 7. Since it was off before, I bet it's off everywhere. Okay, so algebraically, how can we find the limits without a graph? With the graph, it's easy just to kind of look at the graph and see what's happening on the left, what's happening on the right. If you don't have a graph, what do? So one thing you can always do is just plug in x values. Plug in inputs. I should say inputs instead of x values. Plug in inputs. So I'm just going to scroll back up to the very first problem we did so I can remind you what that looks like. Okay, if we don't have this graph, if I did not have this graph over here, I could have gotten the same answer by just plugging in a whole bunch of values from the left and a whole bunch of values from the right and make sure they're doing the same thing. That's plug and chug method. That's technically algebraically, right? Because you're plugging things into the function and you're calculating outputs and seeing if the outputs are matching. Okay, but luckily calculus has some theorems for us, some shortcuts basically. So that you can always do this. If it's the day of the test and I ask you to do something algebraically and you freak out and you don't remember what to do, you can just plug in inputs from the right and figure out what the function gives you, and then plug in numbers from the left and figure out what the function gives you, and then see if they're matching. It's just very tedious to do that, right? But it's algebraically correct. What we're going to do right now is talk about some theorems, some shortcuts. So let me pop up here. Okay, so here are the shortcuts. So think of these cases as shortcuts that are going to help us think about this algebraically. So here's a shortcut. It says if f is a polynomial or rational function. So this only works for polynomials or rationals. That's it. So remember, polynomials are like really pretty quadratics, cubics, something to the fourth power. Polynomials are like really smooth, pretty graphs. They look like this. There's no holes, there are no jumps, there are no asymptotes. They're just really predictable, pretty graphs. If they're really pretty and predictable, you're not going to have any issues. The limit's going to be really pretty and predictable. But if it's a rational function, that's where you have a fraction, right? A rational function is where you have a polynomial in the numerator and then a polynomial in the denominator. So then you could have some issues with the denominator being 0. So anytime there's some domain issue, you might have to do some more work, right? So, but this is what this shortcut says. The shortcut says, if your input is a real number, so here's your input, and you just plug it into the function. If you just take that input and plug it into the function, one of three things is going to happen. If you plug the input into the function and you get a real number, that's the limit and you're done. If you plug a number into a polynomial, you get a real number, you're done. That's the limit. Okay? If you plug that input into the limit and you get this specific fraction, 0 over 0, you have more work to do. You have to simplify the function and then re-evaluate. So I'll show you an example of that. But if you plug that input into the function and you get a non-zero number over 0, that's undefined, right? Then you know for sure the limit doesn't exist. Okay, so let me just show you these three examples, these three little shortcuts. We don't have graphs. Yes, I could put them on Desmos, right? But you'll be asked to do these algebraically, and that means you could use Desmos to check yourself, but you have to support your work with some algebra. So let's take a look at this first function here. This first function, here's my f of x. Isn't that just a pretty polynomial function? It's a polynomial. You can use some ideas from algebra here. This is just a parabola that opens up. It's quadratic. There's no holes, there's no asymptotes, there's no jumps, there's nothing weird happening. So I know this is super predictable. So what we're going to try to do, we're just going to test. We're going to plug this input, x equals 3, into this function. And if I get a pretty number, which I should, that's my limit. And I'm going to check it on Desmos, but this is the algebra part. So let's just plug it in. Let's plug 3 into this function, and since it's a polynomial, it should come out really nice. And I forgot my graphing calculator on my dining room table, so if someone could plug that in for me, that would be awesome. 9 times 5 is 45. Minus 30 plus 7. So was it 20? What did it come out to be? Sorry, I was trying to see in the chat and it's not letting me go over there. 22? Okay, cool. Awesome. 22? Sweet. So the output on this one is 22. Since this is a real number, that's case 1. So that's also the limit. So what I can say here is, since that's a real number, we're at case 1. So that means the limit as x approaches 3 of that polynomial is just going to be 22. That's it. We don't have to do any more work. Since we're running low on class time, I'm not going to graph it. But if I graphed it, the height from the left would be approaching 22. The height from the right would be approaching 22. Overall, the height is 22. That's your limit. And that would be kind of hard to read on a graphing calculator. You'd have to really zoom out to see everything. Even in Desmos, you'd have to zoom out a lot. It's kind of cumbersome, but you could check yourself. But that's the algebra. This is the algebra supporting, it's algebra mixed with calculus, right? It's supporting this algebraically using the theorem. Okay, so let's see some examples of case 2 and case 3 here. Here we go. Okay. So I repeated these instructions. This is probably problem 8 on your notes. So for any of these, oh, I hear a little chime. Oh, it's problem number 7? Okay. Okay, our number's lining up now. That's good. Okay, so remember, for any of these cases, your first step is just to evaluate the function. Just plug it in. So we're literally just going to plug in x equals 4 and see what happens. That's what we're going to do here. So we're going to plug in x equals 4 into this function, and let's see what happens. Okay, so 3 times 4 minus 12 over 4 squared minus 2 times 4 minus 8. Okay, so I'm just plugging it in. And if we get a real number, we're done. If we get a real number, we're case 1 and we're done. Let's see what happens. Okay, so that's going to be 12 minus 12 on top. Yeah, 0 on top is totally fine, but on bottom, we're getting a 0 on bottom. Uh-oh. This is going to be our case 2. See how that matches case 2 up here? Oh gosh, so what do you have to do for case 2? Case 2 says to simplify that function as much as possible, then evaluate the simplified expression. So now here comes some algebra. How are we going to simplify this? So I need to simplify this expression. And how do we simplify polynomials? Well, we can rational functions, we factor them, right? So we need to factor and then see if anything's going to cancel out or reduce. So let's see that. So I'm going to quickly do the factoring here. If you're struggling with factoring or need to dust some cobwebs off, you'll have to review that outside of class, or you can come to office hours. But the first step of any factoring problem is to ask yourself, is there a GCF you can factor out from the beginning? And in the case of the numerator, the answer is yes, right? See how there's a GCF of 3 I can factor out? So I'm going to factor out a 3, and that's going to leave me an x minus 4 binomial. So then I look at my binomial and I ask myself, is there anything else I can do here? Is this a difference of squares? No. Is there anything else I can factor out? No. So we're done. That's been completely factored. Remember, factoring is just rewriting a polynomial to be a multiplication of 2 or more different polynomials. So I have a monomial 3 times a binomial x minus 4 there. So it's factored. Okay, now in the bottom, let's ask ourselves, is there a GCF between x squared, 2x, and 8? So nope, there's not a GCF. So you would either factor this into 2 binomials using guess and check. If that's what your algebra teacher taught you, use guess and check. Or you can do AC method. I'm just going to do my brain power. I'm not going to show the factoring here because it's technically a prerequisite skill. But again, if you need help with that, I can send you some videos or you can find them online. So this is going to be x minus 4, x plus 2 once you factor all that out. This one's easier to do in our head because it has a leading coefficient of 1. But if that had been like a 4 or something, you'd probably want to do your AC method. Okay, so once we do all that, what do you notice here in the numerator and the denominator? Yeah, see how they have this binomial in common? So any number divided by itself, except for 0 divided by 0, any non-zero number divided by itself just divides to 1. And what this is going to give me is 3 over x plus 2. So technically what's happening there is there was a hole right there. Whenever you have factors that divide out, that means there's a hole there. That's where that hole, it's a removable discontinuity is what we call it. There's a hole there. Those are canceling out. That's why you don't see it on the graph, because they canceled out. But if you tried to plug a 4 in there, you'd get a 0 in the bottom. So there's a hole there. So there's going to be a hole at whatever makes x minus 4 be 0. Well, what makes x minus 4 be 0? X would have to be a 4, right? So there's going to be a hole at x equals 4. That's why when I plugged it in, something weird happened. But if there's a hole, there's a chance it could be doing the same thing from the left and the right. There's a chance that could be happening. So what we do now, this is what we've done so far. We have simplified as much as possible. This is my simplified function. Now that we've simplified the function, then evaluate the simplified function. So we need to evaluate the simplified function. Okay, so we can do that. So now I'm going to take 3 over x plus 2, and I'm just going to replace this x with whatever I was supposed to plug in from the beginning. We were supposed to plug in x equals 4. That's what we were supposed to plug in, so that's what I'm going to plug in there. And I heard a little chime, so let me pop over there. No real number. Does it come out to be... Yeah, oh yeah, plug in 4. Okay, so I'm going to plug in a 4 there, so let's go ahead and do that. So 3 over 4 plus 2, that's 3 over 6, that's 1/2. Is that a real number? Yep, it's a real number, so we're done. We're done. That's the limit of this overall function. So the limit of this overall function is going to be 1/2. And I'm going to show y'all that on Desmos because I know this is a lot of algebra for us. So let me, I think it's worth our time for me to pop over to Desmos and just show us this one really quickly. Okay, so let me pop over to Desmos. Share Desmos. Okay, so let me erase the functions we had here. And my new function is going to be 3x minus 12 on the top. Oh. And on the bottom, it's going to be x squared minus 2x minus 8. Okay. So, oops. So let's see what's going on here. I can see there's a vertical asymptote here where x equals -2. So let me type that in real quick. X equals -2 and make that dashed. Okay. So when x equals -2, there is a vertical asymptote. But when x equals 4, let's see what's happening there. If I put 4 into the function, see how it's telling me it was undefined? There's technically a hole right there. There's a hole right there. But what's happening is I get really close from the left. So I'm going to type in 3.99999. See how that's getting really, really close to 0.5, which is 1/2? And then on the other side, if I plug in 4.0001, see 4.999, see how that's really close to 1/2? So as I'm zooming in there, let me dot this one out here real quick. As I'm zooming in on this green line right there, see how at 4, it got, the height looks like 1/2. I grabbed that green line I graphed right there is 1/2. So from the left, it's approaching a height of 1/2. From the right, it's approaching a height of 1/2. But at x equals 4, it's actually undefined. If I try to plug 4 into the function, I get this undefined value right there. Okay, I know that's a lot. How are you feeling? Someone throw some statuses in there. Go to your profile picture, click it. Show me. I don't see your face right now. I have no idea what's happening. Got happy faces, got confused faces. I don't have an unhappy face yet. Yes, Cassandra, Desmos is allowed on quizzes and tests. Just make sure that if the problem asks you to do something algebraically, you're supporting your answer with algebra. You can always use Desmos to check yourself. You can use the graph to check yourself, but the work you have to show to support it would be algebraic work. And that's what I showed here on the notes. So let me go over here and reshare the notes. So the algebraic support is showing all this stuff right here where I simplified as much as possible, all this factoring and canceling, and I got the simplified expression. That's algebraic work. And then I evaluated the simplified expression. All of that is supporting the algebra support. But you could check yourself with the graph to see if you did all that right. Okay, any other questions before we work on the next one? I just noticed my page. Oh, go ahead.
Can you go back to Desmos for a second?
Oh, sure, yeah. Okay, here is Desmos. Okay, go ahead.
Okay, thank you.
Oh, okay, you're just writing something down? Okay. Yeah, if I'm ever going too fast, just ask me to like slow down or pause, or you can do your status with the little slow down symbol. Okay. So, are there any other questions before I navigate away from Desmos? We only have 5 minutes of class left, but there's only 2 problems to do and they go pretty quickly. The rest of the packet was, I thought we would have all this time in the world to do some practice and breakout groups. Whoops. I'll get more used to this time frame, I promise. Okay, so let me go back to our notes. We have 2 more problems to cover and we won't have time for breakout groups today, so that's a bummer. Okay. So let's look, we haven't seen a case 3 yet, right? So, spoiler alert, number 8 is going to be your case 3. So here we go. Okay, all the problems start with just plugging it in and seeing if you get lucky, right? It might be a real number, I don't know. So we're just going to start by evaluating the function. So I'm just going to plug that in right there. So let's start with that. So we are going to plug in x equals -2. Maybe we'll get lucky. So where does the input get sent? In the numerator, I have -2 plus 7. In the denominator, I have 5 times -2 squared minus 20. Okay. So in the numerator, I get 5. And in the denominator, 4 times 5 is 20. You just type that in your calculator if you want. So I get 0 in the denominator. Uh-oh. So it's not a case 1 because this is not a real number. That's undefined, right? It's not a case 1. It's not a case 2 because case 2 has to be a 0 over a 0. And this is a non-zero number over a 0. So we are in a case 3 right now. And it says, if this is the case, if you get a non-zero number over 0, then the limit doesn't exist. You're done. This limit does not exist. So I can jump over here and say the limit as x approaches -2 of that function does not exist. You might see the abbreviation DNE, does not exist. Now, just heads up, in the next section, we're going to go into more detail on what this means. There's different ways you cannot exist, but right now for this section, you just say does not exist. That limit does not exist. So case 1 and case 3 are the nice ones, right? Case 1 is nice because you're done. You get a real number and you're done. Case 3 is nice because it just doesn't exist. Case 2 is the case where you have to do some more work there. Okay. Any questions on this one before we navigate to a piecewise function? Okay, 2 minutes, y'all. We can totally do it. 2 minutes. And just heads up, I'll have the answer key written for the breakout group problems that we didn't have time to do. They were just extra practice. Okay, here we go. One more problem. Is it going to be a case 1, a case 2, or a case 3? I don't know. But it is what we call a piecewise function. So you should have seen piecewise functions in your algebra class. Let's talk a little bit about what they mean. If you need to research a little bit, it's called piecewise function. Okay. What a piecewise function does is it has multiple rules to follow based on different inputs. So in this piecewise function, if my input is less than 3, if that is the case with my input, then I'm going to follow this rule right here. This is the rule I'm going to follow. And for this function, if my input is 3 or greater, so if my input is 3 or greater, then I follow a different rule. I'm going to follow this rule right here. This is going to be the rule that I follow. Okay, so let's see how this impacts our limits. See how my limit is the overall limit? And graphing piecewise functions is challenging. So we're going to do this algebraically. We're going to plug in a value a little less than 3. So plug in a value less than 3. That would be from the left, right? We're approaching from the left. So maybe we'll plug in 2.99. Maybe to be safe, we should do 2.99, and we'll see what we get. And then we're going to plug in a value greater than 3. That's approaching from the right. So we could plug in like 3.0001. And as long as these are really close, they're not going to match exactly, but as long as they're really close, then the limit exists. If they are not really, really, really close, the limit does not exist. And if you're not sure, you just have to plug in something with even closer. If you're not sure, just plug in something even closer. Okay? And there is a shortcut way to do this, but I'm not going to show it to you because this plug and chug method always works. The shortcut is that technically both of our rules are polynomials, so you can just plug it in straight up, but I want to help you understand what a piecewise function is saying, so this is kind of reviewing that. So for this one, I'm going to plug in 2.999 cubed minus 3 times 2.999 on my calculator and see what I get. Except I don't have a calculator. I don't even have my phone with me, y'all. Oh, here's my phone. Okay, let's see what we get there. Oh no, we're over class time. Has anyone done it? Did anyone see what number that comes out to be? I can't believe I forgot my calculator. If you need to log off because you have another class, that's totally okay. Has anyone plugged this one in though? Ooh, 17.97. Did anyone get that? Can anyone confirm 17.9-ish? Yes? Okay, cool. Just want to make sure since it's a weird number. So this is 17.9-ish. Okay, has anyone tried the other one? What's my other rule to follow? My other rule says I take the input, which is going to be really, really close to 3 from the right, square it, and then to 2 times that input. And let's see what we get there. And if those are really close, that would be 3 squared would be 9, and then 2 times 3 is 6. Ooh, is that like close to 15? Yeah, 15. Yeah, so see how those are not matching? 15.08. Are those close to, are those really, really, really close together? Is 18 really, really, really close? Are they matching? No, they're not matching. If they're not matching, that means the heights would be different. There'd be a jump. On one side, it's approaching a height of 18. On the other side, it's approaching a lower height. They're not going to match. So we would just say this limit doesn't exist. So overall, the overall limit as x approaches 3 of this function does not exist because they're not matching. Oh my gosh, you survived another class, y'all. So I will write up the answer key for the breakout room problems. There's no new material there. It's just practice.